Hello, my dear student. I'm Mr. Twala from Educators. I will be with you in physics for Form 5. And today, my dear student, we are going to proceed with our discussion on our topic of rotation of rigid boats for our subtopic of the moment of inertia. So before we proceed with our discussion here, we are supposed to remember where we ended on the last sessions. On the last session, we tried to see the concept of the moment, the concept of the rotation of a rigid body. We tried to see definitions related with the rotation of the rigid body. And after there, we tried to look about the one of the subtopic of this topic, which is called the center of mass. And finally, we looked about the subtopic, the second subtopic, which is called the moment of inertia. And on the moment of inertia, we ended on how we can derive the formula related with the uniform load. And we say that we obtain the uniform load by introducing the integration. We try to say that if we have the uniform load, or if we have the meter rule, and then we allocate the axis of rotation at the center, then we try to rotate that meter rule. They try to rotate and they form the moment of inertia. When we derive by applying the concept of integration, we obtain that moment of inertia is equal to 1 over 12 times the mass of the uniform load times the length square. That is what we tried to see. And after there, we say that let us imagine that the axis of rotation is not at the center. It is at the one end. Now, how can we derive the moment of inertia? We tried to derive the moment of inertia by applying integration, and we obtain that a moment of inertia at the one end must be equal to 1 over 3 times the mass of the uniform load. Then we times by the length. It means the length of the uniform load. So today we are going to proceed where we ended on the last session. We should look about the moment of inertia of a ring through about an axis through its center. Now imagine we have the ring, and that ring we try to rotate. It means that the ring tried to rotate on an axis. When they rotate, how can we get the moment of inertia? What we are going to observe for our today discussion. So once we observe our statement here that consider the mass m, consider the mass of a uniform ring which is m, and also the radius about the axis of about an axis pq, and also passing through its center O, perpendicular to the plane of the ring. That imagine we have the ring, the uniform ring, and that uniform ring, my dear student, try to rotate through about an axis through the center, but they contain the distance. It means from the center to any point where the particles are located inside the ring. It forms the distance. It means that it can produce the distance, the radius that is exact between it. Also contain the mass of the ring. That is what we try to observe. But the ring try to rotate perpendicular to the axis of rotation. It means that they form the angle theta, which is equal to 90 degree. Kwa ilikuwa ni axis of rotation imeact vertically, lakini ile ring ikawa inajaribu kuzunguka around to the axis of rotation. So my dear student, imagine, consider our figure here, number 6 on our topic number 4. We have our figure here, and our figure contains the axis of rotation, which is called the PQ, and also have the center, as we try to observe. This is the center of the ring. But on the ring here, we have the particle. We have the particle at point A, and also we have the particle at point B. Finally, the particle at point C. And we try that all of these particles are joined together through the ring. So my dear student, the particle at the point A contain the mass 1 ambayo tunaita ni M1, and also the particle on the point B contain the mass 2 ambayo tutaita ni M2. But finally the particle at the point C contain the mass 3 ambayo tutaita ni M3. So on the axis of rotation, as we try to observe here, that when the ring try to rotate rotate perpendicular to the plane of the ring, the angular momentum, the angular velocity must be constant. It means kwamba ile angular velocity ambayo itakuwa inatumika pale kuisaidia ile ring iweze kurotate itakuwa and the same for all particles that are found inside the ring. And after there, we say that the distance that exert or the distance that occur between the point A into the center must be equal to the distance that occur between the particle B up to the center, and also the same for the C. This must contain the same distance from the axis of rotation. As the thing that you are supposed to keep into your mind, my dear student, is that the perpendicular, the rotation of the ring through an axis, it means that they occur perpendicular. Ile rotation itaweza kuoccur perpendicular to the axis of rotation. That is what we try to observe. So this is our figure here that give us the concept of the uniform ring tried to rotate about an axis through the center. So after there, my dear student, what we are supposed to know here is that from question number 4.14, the moment of inertia of a small element AB, it means AB on the element A, element B, and also the element C of mass 1, and also mass 2, and also mass 3. They are located at the distance R. As I told you that all of this, the particle A and also particle B, also particle C, they have the same distance from the center or from the point, from the axis of rotation, the center of the ring. They have the same distance. That is what we try to observe. So as we see that on our figure, demonstration in our figure here, that point A must contain the mass 1, lakini point B ata contain the mass the mass 2, but finally point C ata contain the mass 3, as we try to observe here. So how can we obtain the moment of inertia through this point? So the moment of inertia here is obtained by taking by considering each point. It means that we should focus for the point A, point B, and also point C, so as to demonstrate the moment of inertia. So moment of inertia for the point A must be equals to mass 1 times the distance square. Kwa hiyo tuweze kupata moment of inertia kwenye point A pale, tutamchukua yule mass 1 tutamzidisha na distance ambayo ana act pale between that particle, it means the center and also the small elements. So and also in order to get the moment of inertia that occur at the point B here must be equals to the mass 2 times the mass 2 times the distance square. Kwa hiyo tuweze kumpata moment of inertia wa point B atakuwa ni sawa na mass 2, then we times by the r square, lakini huyu r square ana represent the distance between the point B and also the center of the ring. Finally, for the point C here, we obtain the moment of inertia for the point C by taking the mass 1, because at point C we have the mass 3. Now, if we want to obtain the moment of inertia, we should take the mass 3, the mass that are found at the point C. Then we multiply by the distance. It means r square. Huyu r ana imply that this is the distance that exert between the point C and also the center where the axis of rotation occur. So after there, we should record the moment of inertia for the whole ring. Now we have tried to see for each particle that are found through the ring that are joined together. Now we are going to see how can we get the moment of inertia for the whole ring. Sasa ring kwa ujumla sasa inakuwa ina contain moment of inertia ni sawa na ngapi? So my dear student here, we should consider for the whole ring. Now we obtain the moment of inertia by summing. It means that we should take moment of inertia for the whole ring must be equals to the moment of inertia at point A and also plus the moment of inertia at point B. Then we add by the moment of inertia at point 3. Then we add dash at the center at the instance of the particles. Now, if we demonstrate there, we should obtain that moment of inertia for the whole ring must be equals to the mass 1 times r square. Then we add by mass 2 times the r square. We add by mass 3 times the r square. Then we add dash for the mass of the end stems. Then we multiply it by the radius of the ring square. So after this, my dear student, now we are supposed to assume that as because the distance that act between the particles through the center to the any particle that are found inside the ring are the same. Kwa kama distance in the same, we should fact out. Kwa huyu r kwa sababu anapatikana ni boss ni common, tutaweza kumfact out. Tukishamfact out tutabakiwa equation yetu it means kwamba we record the equation number 22 on the topic number 4 here, that moment of inertia must be equals to m1 plus m2 plus m3 plus dash up to the nc terms of the masses. Then we multiply by the r square. We should fact out the radius square or the distance square because are common into our equation number 22 here as we try to observe. So after this here, we are supposed to consider that for individual masses, now we should say that mass 1 plus mass 3, then we add by mass 3, we add by mass 4, then we add by n stems of the masses must be equals to the individual masses. Kwa hizi hapa tutazitemu tu kwamba kwa sababu ni kwenye ring, hizi zinatengeneza masi moja tu ya huli ring. Kwa tutasubstitute ni sawa na m as we try to see here. Now finally we should say that the moment of inertia for the whole ring, for the whole uniform ring must be equals to the individual masses times the distance square. The individual masses is represented by the symbol m as we try to observe. So after there, this should be the equation number 23 on our topic number 4, and we should conclude by saying that for the ring, it means that for the ring, the moment of inertia must be equal to mr square, but m represents the individual masses of the ring, while the r represents the distance of the ring square. So where, as I told you that this sum of the masses here must be equal to m, which imply as the mass of the uniform ring, as we try to observe. So we should conclude by saying that therefore the total moment of inertia of a uniform ring about the axis through the center is given as this one. So after making this mass 1, mass 2, mass 3, and also the n stems of the mass be as the single masses, the mass of the uniform ring. Now we should conclude by saying that the total mass, the total moment of inertia through the uniform ring must be equal to m times the r square, where m stands for representing the mass of the uniform ring, while r square representing the distance of the uniform ring. It means the distance that is exactly from the center up to any point through the ring. So my dear student, after there, let us recall that since dm is the fraction of the total mass, now we should consider that if all the particles that are found inside the ring consist as small particles ambayo tunaita ni dm hii ambayo tunaiona hapa, so dm become at the fraction of the mass of the disk. Kwa huyu dm atasimama ni kama a fraction, wa masses of the disk. So the mass and the area for both the disk here, the mass and the ring can be expressed at this one. So we in terms of the area, we should represent it in form of in terms of the fraction. Now we should say that dm, the small change of mass, as we observe here, divided by it is their area must be equals to the mass divided by the area here, as we observe. So, but the equation number 26 here, the area A of the disk is this one. It's also pi r square. Now we should say that we know that the area of the disk must be equal to the area of the ring. Now we could say that the area must be equals to pi r square. Tunajua kabisa kwamba tulifundishwa kule kwamba hivi sphere inakuwa na area, formula ya sphere ni ipi ya kutafuta area? Tunajua ni sawa na pi r square. Kwa we should because the disk and also the ring are the same with the circle. Now we should say that the formula of obtain the area for the ring or for the disk must be equals to the pi r square. And the area dA of the ring is this one. How can we get the derivative of the ring? Now we are supposed to differentiate this area, kwa sababu tumepata kabisa kwamba kama area wetu ni sawasawa for the small change, area must be equals to pi x square. If we consider the small particles, means that the area become very, very small, we should differentiate. If we differentiate with respect to the x, we could say that this area, small change of the area, must be equals to 2 pi x. Then must be equals to 2 x times the distance. Then equation 26 here can be written as this one. Now we should represent our equation number 26 by saying that dm, by making dm as the subject. Finally, initially we was having the formula of obtaining dm over dA equals to m divided by a. Now we are supposed to make a dm as the subject, the small change of the masses. If we make it as a subject here, we should obtain that dm must be equals to m divided by a. Then we multiply it by dA. But the formula of obtain dA, we try to differentiate for the small change of the area, and we obtain that this dm must be equal to 2 pi x dx divided by pi r square multiplied by m. This should be the equation number 27 here. So after this one, we should conclude by saying that from the equation number 4.5 and also our equation number 4.27, the total moment of inertia here, I, of the whole disk about the axis through its center is given by this one. Kwa baada ya hapo sasa tunachoenda kukifanya hapa, tutaenda kuintegrate. How we are going to try to integrate so as to determine the value of the value of the dm. It means value ya huyu dm, na mwisho wa siku tuende tukamsubstitute pale. So here as we know that the moment of inertia here must be equals to dm times the distance square. But dm tumeshampata hapa, tumeshampata huyu hapa. Sasa tutamchukua huyu, tutaenda kumsubstitute hapo. Kimsubstitute alafu kwa sababu 2m pamoja na r square the same, we should integrate from 0 up to the r ambayo ni x power 3 here. Kwa ukisha integrate hapa, tunajua kwenye kuintegrate kabisa kwamba we should add 1 for the exponent and divide by those exponent that we find we obtained after adding 1. We should integrate with respect to dx. Kwa ukisha integrate hapa, tutakachokuja kupata itakuwa ni x power 4 divided by 4. But the r change, it means from 0 to r, it means kwamba formula ambayo tutakuja kuipata baada ya kusimplify pale, moment of inertia atakuwa ni sawa na half mr square. Kwa hiyo hii ndio formula namba 29 ambayo itatumika kuweza kutafuta moment of inertia ya uniform load. It means ya uniform ring when the ring tried to rotate through the center or about the center of an axis. This we should use. So after this, my dear student, there are some tasks here you should ask yourself that how can you demonstrate, prove that the moment of inertia of the uniform ring must be equals to half mr square. Kwa hiyo utajaribu ni kama task kuweza kudemonstrate hapa. So after this, my dear student, this should be the end of our session here. Now I would like to welcome you again.